Welcome to EDU World Space.
All right. In the ionic compounds lithium fluoride, sodium chloride, potassium bromide, and rubidium iodide, the measured cation anion distances are 2.01 angstroms for lithium fluoride, 2.82 angstroms for sodium chloride, 3.30 angstroms for potassium bromide, and 3.67 angstroms for rubidium iodide, respectively. Predict the cation ion distance using the ionic radii given in figure 7.8. So to figure out the radii, to figure out the bond length, we're just going to add the radii of our two atoms, because remember when we tend to look at a ball and stick model when we're talking about bonding, but in reality, the space filling model is actually more accurate. It's atoms coming together and their valence electrons overlapping, and that's what causes that specific bond. So Uh, for the first one, LiF, we're going to add 0.90 plus 1.19 angstroms, going to be equal to 2.09 angstroms. As for lithium fluoride, now for NaCl, it's 1.16 angstroms plus chloride 1.67 angstroms. 1.16 plus 1.67, 2.83. Angstroms for NaCl. L for KBr, what's it going to be? 1.52, 1.82. That's going to equal 3.34 angstroms. That's going to be that for KBr. Now for rubidium, it's going to be 1.66 angstroms plus 2.06 is going to equal 3.72 angstroms for rubidium iodide. These are the theoretical L-cation anion distances using the ionic radii given. Now, calculate the difference between the experimentally measured ion-ion distances and the ones predicted from figure 7.8. So we're going to subtract these from our theoretical minus our experimental. Sorry, experimental minus theoretical. So 2.01 minus 2.09 is equal to minus 0.08 angstroms. Now, 1.16, sorry, 2.82 In fact, it's just easier to do the other way since it's going to be positive. So 2.09 minus 2.01 is equal to 0.08. So then we get 2.83 minus 2.82 is 0.01. And then we got 3.34 minus 3.30 is going to be equal to 0.04. And then 3.72 minus 3.67 is going to be equal to 0.05. So those are the values between the experimentally measured ion-ion distances and the ones we predicted. You can see that they're fairly accurate. With the ones that we're measuring, those are actually going to be the values we measured from theoretical evidence, that those are going to be slightly higher than what we saw from the experimental evidence, but roughly they are very close. In fact, for sodium chloride, it's almost exactly the same in bond length, both experimentally determined and also theoretically determined. So now they want to know, what estimates of the cation-ion distance would you obtain for these four compounds using neutral bonding atomic radii? So that's going to be pretty simple. So we're going to use these ones in blue. These are the atomic radii for neutral bond for neutral atoms. So 1.28 plus 0.57 is equal to 1.85 angstroms, which is for lithium fluoride. And now for 1.66 plus 1.02 so that's going to be 2.68 angstroms. NaCl. Now 2.03 plus 1.20 is equal to 3.23 angstroms. So potassium bromide. So then for rubidium iodide, it's 2.20 plus 1.39 is going to be equal to 3.59 angstroms. So rubidium iodide. So now these are the estimates of cation-ion distances if we're using neutral atom radii. So now they want to know, are these estimates accurate as the estimates using ionic radii? And just at a glance, you can say no. So using ionic radii helps you overestimate our bond length, and using neutral ionic radii tends to underestimate our bond length. So you can see that, well, here you would have, well, for when using ionic radii, you would have a difference of 0.08 for lithium fluoride. If you use neutral atoms, you're actually going to have a 0.16 difference. That's higher error for neutral atoms. Here you have 0.01. If you're using this one, using neutral radii, you would have a 0.14 difference. For our potassium bromide, you have a 0.04 difference with ionic, and you would have a 0.07 difference with 0.07 difference with the neutral. And for rubidium iodide, you would have 0.05 a difference with with the ionic, and you would have a 0.8 difference with your neutral. Though you'll notice something interesting, and that's the fact that as you're going down the periodic table, your error for using the neutral atomic radii, that's actually starting to decrease. Like lithium fluoride is significantly less accurate than the one for rubidium iodide, which actually is relatively close. That's because that has to do with the fact that has to do with the fact that the since you're losing when you have atoms that are very large, the loss and gain of electrons is not going to affect it to the same degree as you would when you have a smaller atom. Like, although if you get a rubidium ion, like you can see here, the radius is like if you go take an electron away from a rubidium atom and turn it into a rubidium ion, the radius is going to get smaller. Conversely, if you give an electron onto an iodine atom, the radius is going to get bigger. So the loss. So it looks like for larger elements, when you're making this kind of bond, the loss in the radii of the cation is to a large extent made up for by the increase in the radius by the anion. So this seems to happen in the larger elements, but not the smaller ones. Because it has to do with how drastically the taking away of that electron from the cation or giving that electron to the anion has on the overall change in the size of your atom. So again, just to reiterate, the using the ionic radius is actually more accurate than using the radii from neutral atoms.